And we then have a formula that we can use that combines all of these various factors together, and it's probably the only formula I think that you really need from the book. Let's see if I can find my eraser here. I seem to have dropped my board eraser. Just bear with me for a second so I can at least pick up something that I can use to erase the board. Well, we've got to, oh, here we are. No, that's not it either. All right, well, we're going to have to use a, oh, here we go. Use this here. Okay, so we have an equation in your book. It's probably the only one that I think that you're really going to need, which is actually showing us the exposure. It's going to give us the exposure in Roentgens, and this is X. So this is exposure in Roentgens. And this is going to be equal to gamma, gamma A T divided by D squared. Now gamma is the gamma is what we call the exposure rate constant. So this is the exposure rate constant. A is the activity. And that the activity is going to be measured in millicuries. So this is going to be in millicuries. T will be time, which will be measured in hours generally. But we can, this will assume that our rate constant is going to be in millicuries in hours. If our rate constant is given in some other units, then we're going to have to adjust for those other units. And D is distance. And the distance will be in, I believe it's centimeters. Let me just check and see. Yeah, it's usually centimeters. So since it's D squared, it's going to be centimeters squared. So this will be centimeters squared. So we're going to have rate constant. Then the rate constant, for instance, let's see, the unit for the rate constant is given as, let's see if I can find a unit for gamma here. So gamma is it's in Roentgen centimeters, Roentgen centimeters per millicurie hour. So that, yeah, that comes out. So that means that centimeters will cancel out. Everything's going to cancel out except for milliroentgens. The Roentgens will be left. That's the only thing that will be left behind. So if we put in all the values that are in the book, it's 3.27 Roentgen centimeters squared per millicurie hour, and we multiply that by 25 millicuries times 40 hours, and the square of 150, which is what is that? 20. It's 0. No, I don't have my calculator here. 25, 75. 22,500, I think that is, if I did it correctly, or maybe it's 225,000. That's 22,500 square centimeters, and that's going to come out to 0.145 Roentgen, which is 145 milliroentgens. So that is how you do that kind of a problem. Shielding. We haven't talked about shielding, and it's a little bit harder to do shielding. We can actually use, first of all, when we're discussing shielding, we have to realize that you don't necessarily always go for what you would consider to be the best shielding possible in terms of, that this will prevent most radiation from getting through. For example, you don't want to shield using something like lead against something that's going to be potentially producing bremsstrahlung. So for instance, if you're using low Z materials, things like plastic, you can actually shield, you can actually prevent bremsstrahlung production, because high Z materials, things like lead for instance, when they're much more likely when you're dealing with a beta emitting nuclide, they're much more likely to actually produce bremsstrahlung. So, for instance, if you had tritium, you might want to encase it in plastic. That would prevent bremsstrahlung, and at least it wouldn't totally prevent it, but it would minimize the amount of bremsstrahlung production. And any bremsstrahlung that got out of that, you could then actually encase the entire thing in lead. That would prevent the X-rays from actually coming through the lead. But if we started out just putting everything into lead instead of encasing it first in plastic, we'd have a lot more bremsstrahlung produced, and some of that X radiation might actually get through the lead shield that we're using if we weren't using something that was very thick. So this is what I mean about actually looking at the very specific kinds of radiation in order to actually design the type of shielding that we're going to use. And we've got another example in here that uses, it's just showing us how we can actually calculate, well, this goes back to something that we had talked about before, which were half value layers and 10th value layers. So it's saying the question is how much lead is needed to cut the exposure we've got an example. Let's see, it was talking about the previous example, the one that we just did. So we've got, it's a cesium 137 beta emitter, and we want to look at the gamma rays that are being produced. So mu for this particular example is 1.07 reciprocal centimeters for lead exposed to gamma rays from cesium 137, and then we can actually use the relationship ln I sub 0 over I equals mu times x, where x is actually the thickness that we're trying to find the thickness of materials, and so we get the natural log of 145 milliroentgens, which was actually the amount in this previous example. We found 145 milliroentgens, and we want to know so that's our I sub 0 value, and that's the amount that of the radiation that's actually produced at the source. The amount that actually gets through that actually is getting through the shielding, or we want to cut it down to 2 milliroentgens. So that's the I value. So the ln of 145 divided by 2 equals 1.07 reciprocal centimeters. That comes out to 4.0 centimeters is the thickness of a is the half value thickness. So how many half value layers does that correspond to? It corresponds to, since a half value layer is calculated to be 0.65 centimeters, that's remember, is the amount of thickness that we would need to reduce the value from 145 milliroentgens to half of that value, which would be 72.5. So this is actually equivalent to 6.2 half value layers. If we do this, we can also do this as 10th value layers, and we find out that that's equivalent to 1.8 10th value layers. So that's 1.8 times the thickness we need to reduce this to 1/10 of the value. That is to reduce it from 145 to 14.5. We can incorporate shielding in the exposure equation in this equation that we had here, because shielding, we can put shielding in just entering the unit B, where B is the transmission factor. So now we can actually expand our equation a little bit further. Seem to have every time I put my my board eraser down, I can't seem to find it again. Well, I'm just going to write it in here. Here's the B, and that's the that actually is the transmission factor, and B is that factor of I divided by I0. So that's B, and that really that equation really gives us everything that we need to do any kinds of calculations regarding exposure and the amount of the thickness of shielding that we would actually need. So there is another example in your book, and I'm not, and again, I don't expect you to know to memorize these mathematical equations outside of possibly this one, but I don't think I'll actually give you you should at least know what the terms are that are in here. So we've got exposure constant, activity, time. These are things that are all going to be the shielding. All these things are directly proportional to this, and then the distance is an inverse relationship. So you should understand all of those things. That's pretty much what we've got in this chapter. Wasn't really, it's a relatively short chapter, so I appreciate again your attention to this material, and next week will be the last lecture, and we'll continue after that with some lectures, I think, in some Judaic related material that Rabbi Weiner is going to give you. Again, thank you for your attention.